All right, now following after, where did we leave off? I forgot. 1909 was not Planck. It was Geiger and Marston and Rutherford's model. Okay. We now follow in 1915. So we had the Michelson-Morley experiment that proved, that light does not need a medium for which to travel through, which sets up Einstein in 1915 for development of the special relativity. He talks about, at this point, he can talk about light not needing a medium, but more importantly, he develops his two postulates. He gets rid of this long-standing belief. That predates to Newton, that there's a primal reference frame. One of his two postulates is that there is no preferred reference frame. So that eliminates that Newton's belief that there is a prime reference frame. That, sort of that alchemaic, I don't know the exact word for this, the alchemist type belief that Newton had about primal reference frames, that there are the origins of the universe are in that primal reference frame. So we eliminate that, and we have Michelson and Morley proving that light travels at 3 times 10 to the 8, regardless of what. So you've got the formation of the relativity laws. Now, Eddington in 1919 performs an experiment in Africa using an eclipse that proves general relativity. That whenever you introduce a massive object in space, that object warps space and time. So what we have is we have the sun, and we have a star situated behind the sun. Well, when the eclipse happens, originally the star appears to be over in this region because it curves like this, but from our eyes we believe it to be like that. Once the eclipse happened, we knew that the location of the star is not in this region. It would have been avoided. It would avoid the because light's being bent around it. We don't see the star anymore. I do believe that. Eddington proving general relativity. 1820 physicists of all time, Niels Bohr, develops the Bohr model. So Bohr model compared to the Rutherford model. So the Bohr model says that you have discrete shells, and whenever you take energy away, an object would be here at one point, but then all of a sudden it would be here at another point. It doesn't travel the distance in between. It simply is here and then here. And now that's being backed up by Planck's constant, because these orbitals turn out to be multiples of Planck, well, it's Planck squared. But it's being supported by Planck's constant. Okay? Now, remember Rutherford's model says that you can have any sort of orbital, it doesn't really matter, and when you take energy away, it just degrades into a smaller orbit. So those are the difference between the two, is that these have particular orbital values, and these particular orbital values are some sort of Planck constants that are in there. Rutherford says that there are no particular orbital values. This one states that once energy is removed from an electron, it drops instantly, not traveling the distance in between from one orbital to another, while this one decays slowly like planetary motion. Okay? So you get the development of Bohr and Bohr's model, which Einstein and Bohr eventually fight over it. Okay? We have de Broglie, 1924. De Broglie publishes his doctoral thesis on the wave property of matter. He says matter has a wave property, and that wave property is related to its momentum. Okay? So you get 1924, where we're starting to see, oh, look, not only do we have to worry about everything being a wave, we have the introduction of the idea of matter being a wave. Okay? Heisenberg, 1925, develops the Heisenberg uncertainty principle. He says that observations affect the outcomes, okay, which is a nice introduction. It's a nice way of, off on a tangent on that one. It's quantum mechanics again. We're talking about how well we can measure something with a degree of certainty, and how that measurement in itself destroys information. Okay? 1927, Compton's experiment, or what's called Compton's scattering. We discover something phenomenal. Light has momentum. Okay? Compton fires an electron, or not an electron, a photon, at electrons. There's my electron, and when they collide, you get the electron to change its direction. Okay? So an electron's moving, a photon's moving, that photon strikes that electron and changes that electron's direction. Okay? It collides with it, it's momentum. So Compton discovers momentum. That light has momentum, sorry, not momentum. But light has momentum, but no mass. Also, 1927 is the Copenhagen interpretation. I just left it abbreviated. The interpretation is a conflict between Bohr and Einstein. The break between them is 1927. You have Einstein still a classicalist. He still believes in Newton's laws, even though at this point we're looking at the photoelectric effect and we're seeing that we're getting these properties of H coming out of it. We're looking at de Broglie and waves, or matter has waves. We're looking at Heisenberg and how measurements destroy information, not a classical model of the universe. So Einstein is in conflict with all of this. Well, all of this. Okay. When he goes 1927 to Bohr and has a conversation about the future of physics, well, Einstein says to Bohr, well, God doesn't play dice, talking specifically about Heisenberg's interpretation, this uncertainty that we can never know the momentum of an object, and nobody knows the momentum of an object. So it's kind of a random nature of that sort of stuff. God does play dice. So that's what the interpretation is all about. It's like God. Okay, when you hear God plays dice, it's referring to Heisenberg and Bohr, who's Heisenberg's mentor, defending the Heisenberg uncertainty principle, that there's a play in every value of the universe, that when God created the universe, he created a randomness in the universe, and the events just sort of fell out the way they did, where Einstein, believing in a grand scheme, or believing in the classical model, one event leads to all these other events, but if you know the information of the one event, you know the information of everything. Okay? Cool? Just a little piece of trivia there. Then you have Schrodinger, 1933, releasing the Schrodinger equation. As I said, I'm talking about when I talk about Schrodinger, equation that predicts the motion of particles, but doesn't necessarily give us an understanding of why those particles behave the way they do. Okay? So that's basically the rundown of modern physics. There's certainly more events that happen after 1933. There's certainly more events that happened before 1887, but from 1887 to 1933, you have the bulk of the important items that lead to the of relativity. I mean, modern physics develops in a very short period. Anyway, that's the history of modern physics.